Okay, good morning, everyone. I want to welcome you to another Theory of Statistics class. Of course, the focus, what we're going to be focusing on today is very, very crucial to the course and to the final general. And I will advise that you pay attention. I'm actually going to also, in addition to walking you through the theoretical provision, I'm also going to, uh, highlight area of application as well. I want to welcome you to data method. And of course, let me just give you the background. So what is our intention using data method? Now, let me start. Let me go historically. Actually, we want to figure out the true value of a parameter. A parameter is a population characteristic value that we seek to determine. Parameter could be population mean. Parameter. So when I say parameter theta could be population, could be population mean, it could be population variance, it could be population proportion, okay, and so on like that. So, but you know what? Because we do not have enough resources to go around the whole population, we are limited by budget. We normally take a sample, okay? Normally take a sample. When you take a sample, you actually want to estimate this from the sample, okay? Now, and you need a formula to estimate from the sample. So I'm actually calling that this is an estimator, okay? And you know what? We actually going to, instead of us to get the mean, population mean, we're going to get sample mean. Instead of us to get population variance, we actually going to have the sample variance. Instead of us to get the population proportion, we actually going to have the estimate of that. So this actually came from sample, why this is the population. Okay, so like I said, this is parameter, okay, parameter, okay. So this is a parameter, why this guy is an estimator. That the guy is an estimator. So this is what happened. By parameter, we mean a population characteristic value. Go ahead.
Did you just say that the estimator is a function?
Yeah, estimator is a function. Estimator is a function like if I want to get this guy, if I want to get this, I'm actually going to say it's a function of S. Okay? If I want to get a variance, there's a formula for that. If I want to get a P cap, there's also a formula for that. That's a good question. If I want to get this, then we have a formula. We have a formula for that. Okay? Maybe I want to estimate the proportion of those who actually have a disease. Okay? If N is the number of those tested, the number of people tested, X is the number of those that actually test positive to disease. So this is an estimate. So now there's something I actually want you to see. There's a when we can't get parameter directly. To get parameter directly, we need the whole population. When we take a sample, we're actually going to use estimator. Now, because of that, we're actually going to say whenever sample is involved, estimation is involved. Estimation is involved. Estimation is a process through which we get unknown population parameter value through sample information. Okay? And the formula that we use is what we call estimator. Now, and I want you to pay attention now. By central limit theorem, we are told, by central limit theorem, we are told that sample mean, okay, we follow normal distribution, okay, with the mean of this and the variance of that. This is by central limit theorem. By central limit theorem, we mean when, when n is large. Okay, when n is large, this is actually going to happen. The distribution of the sample mean, we actually follow this. So what this guy is trying to say, the expectation of this equal to mu, the variance of this equal to sigma square over n. This is by central limit theorem. Now, it is not all the time that our estimator is going to be this. Our estimator can be a nonlinear function. Okay, for instance, what if in a situation where I want to talk about a function of a sample mean? Please pay attention. We've been talking about, by central limit theorem, we understand the fact that when n is large, the distribution of this guy is going to follow normal, even if that was sampled from a non-normal population. Okay, even if I have from exponential, or I have from gamma, or I have from beta, I have from wherever distribution, we believe that when n is large, okay, the mean will follow normal distribution. So this is now going to be the mean of that distribution. Then the sigma squared will be the variance of that distribution. But what if in a situation where we're not working with a sample mean, but we're working we want to focus on a function of a sample mean. Now, if I want to focus on a function of a sample mean, of course, that is a nonlinear, a function of a sample mean could be the logarithm of a sample mean. It could be reciprocal of a sample mean. It could be square root of a sample mean. It could be whatever function, we could have whatever function of a sample mean. Now the question now is, how can we determine the asymptotic behavior? When I say asymptotic, asymptotic normality means the distribution of a variable become normal when sample size is large. That's what we mean by asymptotic normality. Now, how can we derive the asymptotic normality for the function of a sample mean? And that is why we need a data method. The data method will actually provide us opportunity to derive, to investigate the asymptotic normality of a function of a sample mean. Now, and this is how it's actually going to be. And I need you to pay attention. I need you to pay attention, okay? Now, I know that this follows normal when sample size is large. Then x bar minus mu also going to follow normal, okay, with a mean of 0, okay? I'm still going to have this guy. Please pay attention. How do I get that? Okay, I'm taking advantage from here. When x bar follow normal distribution with this as the mean and this as the variance, the difference between the sample mean and the population mean will follow normal with the mean of that. If I really want to investigate, I can do this. What is the expectation of x bar minus mu? Let me tell you this. Mu is a parameter. Okay, mu fall under parameter. Parameter is assumed to be fixed. Parameter is a constant. Parameter is not subject to variation. But do you know what is subject to variation? What I have here is all subject to variation. But these guys are not subject to variation. Now, if I want to figure out this is going to be expectation of this guy minus the expectation of mu. Okay, now, because mu is a parameter, okay, I'm actually going to have expectation of a mu is a mu, because mu is a parameter. What is the expectation of the x bar? Expectation of the x bar is mu. So what I'm having, okay, I'm having that the expectation equal to 0. That's why you have this 0 here, okay? That's why you have this 0 here. Now, let's talk about the variance now. The variance of x bar minus mu, okay, I want to figure out the variance of x bar minus mu, because a mu is a constant. This is the same as the variance of x bar. Do you agree with me? Because this guy is a constant, okay? The variance of a constant is 0. So I'm actually going, and what is this guy? What is that guy? It's sigma square over n. It's sigma square over n. Take a look at that. And that is why we have this. Okay? Now, if I have for that, I can also continue. What if I multiply by square root of n? I multiply this guy by square root of n. And I want to know the distribution. Okay, I multiply this guy by square root of n. I want to know what is going to be the mean and what is going to be the variance. Okay, what I can do, I can find what is the expectation of the square root of n, x bar n minus mu. I want to get the expectation first. Okay, so now this is going to be square root of n, expected value of that, minus square root of n, expected value of mu. Okay, this is square root of n. Okay, expected value of that is mu minus mu. This is still going to be 0. So the mean is still going to be 0. Now I want to talk about the variance. Like I said, this is very, very crucial. If you don't understand, ask me a question, okay? Now if I want to find the variance now, I want to find the variance of square root of n, okay? I want to find the variance of square root of n, x bar minus mu. Okay, x bar minus mu, okay? Don't forget, anything that come out of the variance, a constant will be a squared, right? I'm actually going to have this guy squared, then I'm going to have the variance of x bar mu minus that, right? And this guy is going to be n, okay? Now here, this guy is the same thing as the variance of x bar because mu is a constant. Then here I'm actually going to have n. What is that? Sigma squared over n. Don't forget, the variance of x bar is sigma squared over n. N cancel n, okay? Finally, is sigma squared. So here is 0 and sigma squared. I need you to pay attention. I want to do this. Number 1, x bar follow normal distribution with the mean of that and that. Number 2, the difference of the sample mean and the population mean follow normal distribution with that. Number 3, when I multiply by square root of n, the distribution is 0 and sigma squared. Let me tell you this. The data method is actually going to rely on this property. Okay? I'm going to show you how for the data method now, because for you to understand the data method, you need to first understand all of this. The data method is going to build on this. Okay, now, before I clean this up, this is very, very crucial. What you have here is a parameter. Parameters are true value. They are constant. They are not subject to variation. But what I have here is estimator. Estimator are random variable. They are subject to variation. I just want you to know that. Okay. Now back to the data method. Back to the data method. Okay. Now, in data method, we actually, by our data method, we're seeking to get the asymptotic behavior of a function of a sample mean. We want to get the asymptotic behavior of a function of a sample mean. Now, the data method actually use the knowledge of Taylor series, because what Taylor series is trying to do is to have a approximation, polynomial approximation of a complicated function, and of course the function of a sample mean will be complicated. Okay, now I want to do this by Taylor series. Okay, the data method uses a Taylor series where this guy is actually going to be equal to the g of mu, okay, plus the g prime of mu x bar minus mu, okay, raised to the power 1 over 1 factorial plus the g prime prime of mu x bar n minus mu squared over 2 factorial, okay, plus the g prime 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 of mu, okay, x bar n minus mu raised to the power 3, okay, raised to the power 3 divided by 3 factorial, and this guy will continue to go all the way to infinity, okay? This is a Taylor series. Okay, now what do we want to do here? We want to have a Taylor series. We want to have a way to approximate the function of a sample mean, okay, using the data method, use idea of a Taylor series. But you know what happened? Anything from second order and above, please pay attention. Anything from second order and above, what I mean, if I want to rewrite this, I'm actually going to have the g of this equal the g of mu plus g prime mu, okay, x bar minus mu, okay, plus, let me say, when I start from 2 to infinity, okay, the g r, okay, of mu, okay, x bar minus mu raised to power r divided by r factorial. If you take a look at this guy is trying to say from second derivative and above. From second derivative and above, we normally write that as this, okay, which actually going to tend to 0, okay? It's going to tend to 0, and because of that, we're only going to be needing, we're going to say this is approximately g of mu plus g prime of mu x bar minus mu. Take a look at that. This is what we're just going to use. Now, you know what we're trying to say? The function of a sample mean is approximately, if this is an estimator, this would be the parameter. This is a function of sample mean. This is a function of population mean with this difference. Now, if you take a look at what I have here now, take a look at this now. I want to investigate the asymptotic normality of this guy. Okay, for me to investigate asymptotic normality of this guy, it means I actually care about what is the behavior, what is this, what is that. Now, pay attention. If I write this, minus this, bringing this guy here, you know I'm going to be left with this. Can you see that? I'm going to be left with that, right? If I'm left with this, if I have this minus that equal to that, okay, if I take the expectation now, what is the expectation of this guy? What is the expectation of this guy? It's going to be expectation into g prime of mu, okay, x bar minus mu, okay? And let me tell you this. Anything that has to do with mu is constant. It's actually going to be taken as constant. So here, this is going to be g prime of mu, expectation of that. Please pay attention. You can see now? What is the expectation of that? I think I cleaned it up. The other time, I wrote something here. What is the expectation of this guy? Who can remind me? What is the expectation?
The expectation of that guy is,
the value. Just give me the value. 0. Is that what we said? 0. Expectation of this guy is 0. Then this guy is going to be 0. It means if I'm interested in knowing the distribution of this minus that, the mean is going to be 0. Now, let's look at the variance. Now, let's look at the variance. Now, the variance of g x bar minus g of mu, okay, is going to be the variance of this guy, x bar minus mu. What is going to happen? This guy is going to be a square, right? G prime of mu, all squared, variance of this guy, right? Of course, you know the other time. You know the variance of that. That's what you tell me? What is the variance of this guy? What is the variance of this guy? Yeah? Thank you so much. Sigma squared over n. Can you see that? If I now want to rewrite, I'm going to say this guy minus this guy, okay, follow normal with the mean of 0, and the variance is this. Can you see that? That's my conclusion. This follow normal distribution with the mean of that and the variance that. Can you see that? Now, I want you to see something now. If the difference follow normal distribution with the mean of that and the variance of that, let's talk about this guy. This guy will follow normal distribution with the mean of this. This will be the mean and with the variance of this. This is data method. This is what data method derived for us. Data method derived that the function of a sample mean follow normal distribution with the mean of this, and this is the variance. Does that make sense?
Normality goes away.
What goes away?
So the normality goes away, right?
Oh, the normality is here. This one follows normal distribution with that. Normality doesn't go away.
It's not asymptotic.
It's asymptotic. We are all, everything here, we rely on what I said when I said, we rely on central limit theorem. This is what happened. The sample mean follow normal distribution by central limit theorem. Then, you know what we're trying to say? Function of sample mean will behave the same by data method. If sample mean follow normal distribution, then the function of sample mean will also follow normal distribution. That's what I'm trying to say here. Now, take a look at this. Okay, that is what I've been deriving. Now, that is that. Now, I want to walk us through this. I need you to pay attention now. I want to go practical. I want to go practical. Pay attention now. Suppose x1, x2 up to xn follow geometric distribution with parameter p, random variable, and we have a sample mean. The question here say, what is the approximate normal distribution of this guy? Can somebody look at this guy? What is that? That's a function of sample mean, right? If we want to know, then I have to use this formula here. And I need you to pay attention. Now, I need you to pay attention now. Central limit theorem. Then, you know what we're trying to say? Function of sample mean will behave the same by data method. If sample mean follow normal distribution, then the function of sample mean will also follow normal distribution. That's what I'm trying to say here. Now, take a look at this. Okay, that is what I've been deriving. Now, that is that. Now, I want to walk us through this. I need you to pay attention now. I want to go practical. I want to go practical. Pay attention now. Suppose x1, x2 up to xn follow geometric distribution with parameter p, random variable, and we have a sample mean. The question here say, what is the approximate normal distribution of this guy? Can somebody look at this guy? What is that? That's a function of sample mean, right? If we want to know, then I have to use this formula here. And I need you to pay attention. Now, I need you to pay attention now. I want us to quickly apply this. What is this guy trying to say? In this class, I walk you through geometric distribution. Geometric distribution is actually used to model events where you have several attempts before you record first success. I want to apply this in two areas. Please pay attention. Two areas. I want to apply that in sports. How many of you play sports here? Or how many like sports? Good job. I also like sports. Okay, I'm also going to apply that in marketing. Please pay attention. Now, a particular basketball coach actually wants to determine the shooting efficiency of his players. And he's going to ask his players to make an attempt. Does that make sense? The player is going to have several throws before they record the success. Now, if the coach wants to determine, what I call shooting efficiency, It's actually going to use an estimator. Now the coach wants to use this guy as an estimator. Does that make sense? The coach wants to use this. How do we derive this estimator? You don't need that in this class. If you want to know how we derive this estimator, then you need to register for 5102 or 4102. Does that make sense? But this is a module. The basketball player wants to, a sport analyst, maybe that happens to be maybe a data scientist or statistician, has already put forward. Now, with this, the coach will be able to measure shooting efficiency, and there's a certainty around shooting efficiency. That's why we need a normal distribution, because when that followed normal distribution, we will be able to construct a mean of testing hypothesis about what is the shooting efficiency of. There's a particular player that played for, is it Golden State? Stephen Curry. Has anybody heard about Stephen Curry, right? You normally make a lot of 3 points. If I want to determine as a coach what is the shooting efficiency, I'm actually going to use this. Now I want to walk you through how to do that. Pay attention now. The question asks, what is the asymptotic normality of this when this guy is large? This is what I'm actually going to do. In that regard, my g of x bar is this. That's my g of x bar. If my g of x bar equal to this, the very first thing, don't forget, by data, please, when something like this comes out in exam, by data, you're going to write the g of this must follow normal distribution with this, and g prime of mu or squared sigma squared over n. You're going to write that one first. Now, if the g of x bar equal to that, then you're going to write your g of mu will be 1 plus mu. That is the first thing. Look at that. If the g of x bar equal to that, the g of mu equal to that. Now, the g of mu is 1 divided by 1 plus mu. Then I need the derivative. What is the g prime of mu? I want to differentiate this with respect to mu. Now, this is the same thing as 1 plus mu raised to power negative 1, right? So if I differentiate that, I'm actually going to have 1 over 1 plus mu squared. This equal to that. Now, if I have this guy, please pay attention. What is the guy telling me in the data formula? Square that, right? I'm going to square that. When I square that, this is going to be this. Can you see that? This guy is that. And this guy is that. I have my g prime of mu squared equal to that. Now that I'm going to put here. But you know what? Please pay attention. Please pay attention. It's getting critical now. If you don't understand, ask me a question. Now, if I want to rewrite this, I'm actually going to say the GS bar of that follow normal. What is the G of mu? It's 1 over 1 plus mu. Then what is this guy? This one squared. Is this guy? 1 divided by 1 plus mu raised to power 4. Then sigma squared divided by n. Do you see this? Do you see what I have? But this is halfway done. I'm not done. This is halfway done. Is there anyone in this class who doesn't understand how I got here? Is there anyone who doesn't understand how I got here? Is there anyone? Look at that. Look at the way I started. Look at the way I started. And I got here. But I'm not done. I'm not done. Do you know the next thing I'm going to do now? Mean sigma squared. I have to use the mean and sigma squared of the distribution they mentioned. What distribution did they mention? Geometric. Does that make sense? Now, and I need to recall that if first follow geometric with parameter p, mu, which is the expected value of s, is 1 over p. We did that in this class. Then the sigma squared, which is the variance of s, is actually 1 minus p over P squared. Do you remember that we did that in this class? Okay, you now know what I'm going to do right now. Wherever I see mu, I will plug in 1 over P. Wherever I see sigma squared, I'm actually going to plug in that here. Now, finally, I'm actually going to write, okay, this. Okay, now, before writing that, maybe what I can do, I want to write this one how? 1 over 1 plus mu. I want to plug in the mu now. So 1 over 1 plus 1 over P. You have to do algebra. I want to do algebra now. Okay? Here, P, or P plus 1. Okay, this is going to be P over P plus 1. Finally, this guy will give you P over P plus 1. That is what I'm going to put here. Now, on the other side, now, on the other side, for sigma squared, okay, I know sigma squared is going to be this guy. But let's talk about 1 plus mu raised to power 4. Okay, that will be 1 plus, what is mu? Mu is 1 over P. 1 over P, okay, raised to power 4. So here, if you find the SEM, I'm actually going to have P. That will be P plus 1 raised to power 4, which is going to be P plus 1 raised to power 4, that. If I finally want to write this, I'm now going to say, therefore, the G prime of X bar is actually follow normal distribution. Instead of 1 over 1 plus mu, I'm actually going to have this guy, okay, comma. Now here, 1 divided by, instead of this guy, okay, instead of this guy, I'm actually going to have this guy, okay, P plus 1 raised to power 4, P4. Instead of sigma squared, I'm going to have this guy. I'm going to have 1 minus P divided by P squared. And don't forget the hand. I'm going to put the hand here. Now, and I want to simplify. Okay, this is going to be this, or P divided by P plus 1. Of course, this guy is going to go up. P4, P plus 1 raised to power 4, 1 minus P raised to power P squared n. Okay, I can reduce this guy. So finally, I'm actually going to have this, or P divided by P plus 1, comma, or that cancel that, or P squared 1 minus P divided by P plus 1 raised to power 4n. This is the final answer. Let me see something here. Now, let's see where we go. Can you see that? Can you see that? That's final answer, right? Can you see the final answer, right? Or P over P plus 1 or 1 plus P the same. P squared, 1 minus P. Can you see that? That is the final answer. Now, this is what the coach is actually, the coach is now saying the shooting efficiency has a true mean of this, and this is the true variance. Why? What is the estimator? The estimator is this. So the estimator here follows normal distribution with the mean of this and the variance of that. In marketing, they can also, if a marketer wants to know how efficient is a marketing campaign, because before you go to record for a serious buyer, somebody that will buy for the first time, you're actually going to come up with a lot of customers that will not buy. Now, if you want to measure how efficient a marketing campaign is, I'm actually going to use, this is an estimator. This is going to be my estimator. If I want to test whether the marketing campaign has increased, maybe it's more than 70%, then if I want to test, I'm going to use this as the mean. I'm going to use that as the variance. Go ahead.
So you called that a model, and you also called that an estimator. Can you kind of clarify how to kind of know that something is a model or an estimator?
Okay. Actually, it's beyond this class. Where this model, we derive it. It's another topic by method of maximum likelihood. And that will be done in 5102. But do you know the assumption that I'm having now? We already have a model in place. We are zooming in this class. We have a model in place. But the model that we have in place is a function of what? A function of sample mean. So when sample mean follow normal distribution asymptotically, we are actually using a data method to investigate the normality of the function of sample mean. Does that make sense? Mm-hmm. Okay, go ahead.
So to get our point estimates, we use this one, not that one.
Do you say point estimate?
Yeah.
Okay, that's a very good question. If I'm only interested in point estimate, I don't need all of this. This will give me point estimate. Do you know what we mean by point estimate? When an estimator gives a single value results. But that is not reasonable because the estimator we use varies. We can't rely on point estimate, and that is why we need an interval estimate. But for you to have an interval estimate, we need this guy. In interval estimate, we need the variance of the estimator. This guy here is the variance of this estimator. Because if I want to test hypothesis or I want to construct a confidence interval, then I need this. So it doesn't make sense in research to just have a point estimate that may be wrong or right, that may be low or high, and that is why we are incorporating uncertainty into the situation because we live in a stochastic environment. That's a good question. Okay, I want to go to something else. Another one. Take a look at this. Suppose X1 follow beta distribution. A sample mean actually is asymptotically normal. They now want you to do this. Look at this. Do you see this? That's a function of sample mean. They want us to investigate this. Does that make sense? Now, look at the underlying distribution, beta. When do we use beta distribution? We use beta distribution when the random variable is in the range of 0, 1. For instance, you want to consider, refinery efficiency. I think I mentioned that example on Wednesday. In refinery, they convert crude oil to usable gasoline. It is not all crude oil that will be converted to gasoline. And that is why we're actually going to have a range from 0 to 1. Now, if a refinery engineer or a petroleum engineer wants to determine the refinery efficiency, let me tell you this. Refinery efficiency, how you convert, there's something that in chemistry they call fractional distillation, how you convert a crude oil to gasoline depends on so many factors. Depend on, number one, the quality of the crude oil. Number two, the temperature, the pressure that you adjust. Number three, you talk about how you maintain your refinery, okay, and so on like that, and the catalyst. There's something that I call catalyst in chemistry because reaction is taking place and you need something to speed up the rate of the reaction. So now, if you take a look at it, if X1 here now, please pay attention, if X1 is the percentage of crude oil converted to gasoline in day 1. S2, the percentage of crude oil converted to gasoline in day 2. The refinery has a record of the percentage of gasoline converted to crude oil in each day. That becomes a random variable, and that follows normal distribution. And right now, the model that the petroleum engineer has developed, okay, through the method of maximum likelihood, to be able to measure the refinery efficiency is this model. You know what we want to do now? This model, without asymptotic normality, we will only be able to get a single value, a point estimate. We don't want a point estimate. We want an interval estimate, and that's why we want to investigate the asymptotic normality of this. Please pay attention. To do that, I want to use the data method approach again. Take a look at that. Now, the g of x bar actually gave it to be log of x bar minus the log of 1 minus that. Okay? This is what I have. And you know what? if this is what I have, I can rewrite this as this, mathematically speaking. Do you agree with me? Mathematically speaking, I can write that as that. The difference of log is the log of the ratio of the two terms. Take a look at that. Now, if I want to do this, I'm actually going to start again and say, okay, G mu equal log mu over 1 minus mu. The same way we started here. G of S bar equal to that. We said G of mu equal to that. We plug in mu for the that. Now, right now, what I actually need to do is to differentiate. Okay, now, this is the same thing as log mu, log 1 minus mu. So these are natural log. Okay, now let's look at the derivative. Okay, what is the derivative of a natural log? That's 1 over mu, right? It's a natural log, 1 over mu. Okay, what is the derivative? What is the derivative of this guy? If I want to find the derivative of this guy, if I actually, this should be 1 over 1 minus mu. Why do I have that? So if I bring this one down, okay, now, if I have 1 over that, if I differentiate this guy, times that, that's how I have a plus. Okay, now let me see right here. Okay, so now if you look at, that's exactly what I'm trying to say here. And when you try to simplify, okay, when you try to simplify this guy, mu into, there's a lot of algebra here. Okay, so this is going to be 1 minus mu, okay, plus mu. Okay, the G prime of mu is going to be 1 over mu, 1 minus mu. Okay, when you do the algebra, we have this. And when we have this, take the square. Take the square. What is the square of that? That will be 1 over mu squared, 1 minus mu all squared. Okay, now you take the square of that. Now, the next thing you're going to do, pay attention now. I need you to pay attention now. Okay, please pay attention now. Oh my God, something like this is coming out in the final. The probability that it's going to be in the final is 1. Something like this. I need you to practice, okay? It's going to be in the final, something like that. Now, I have, so if I want to write now, I'm actually going to say by data, okay, the G of X star, follow normal, the G of mu, okay, the G of mu, the G prime of mu squared, sigma squared over n. Now, I'm actually going to say right now that follow normal, what is the G of mu? So what is the G of mu? Where's the G of mu? Where did I start? Oh, not that one. Where's the G of mu? Okay, this guy. Log mu, 1 over that. What is the square of that? 1 over mu squared, 1 minus that squared, okay, and sigma squared. At this junction, can somebody tell me, what am I going to do next? Exactly. Now, I will now go to the underlying distribution. Please pay attention. What was the distribution? Beta, right? Now, you remember now, you remember here, it said hex follow beta with parameter theta 1. But quickly remember this. In class, I give you S follow beta with parameter that. What is f of s? Based on the one we did in class. The f of s is going to be x to the power alpha minus 1. What's happening here? Minus 1. 1 minus s raised to the power beta minus 1 divided by b of alpha beta. But right now, it's like theta equal to alpha, beta equal to 1. Based on what they gave me. That's equal to that. So I'm going to plug that in here. When I plug that in, okay, I'm having that, okay, and if I plug this guy here, 1 minus 1, then I'm having theta 1, okay, so this is going to be just this divided by this. But you know where I'm going? You know where I'm going? Where I'm going is, in this distribution, what was the mean? You remember in class, we said this, right? The mean is alpha over alpha plus beta, right? That was what we said in class, right? What was the variance? Is it this guy? One second. Yep, that is it. Now, do you not know what happened now? Because what we're looking for, the mu, the sigma squared, that we're going to plug in here and plug in here. Now, here, since we know this is alpha over alpha plus beta, and theta equal to that, then it means I have theta divided by theta plus 1. Okay, theta. Then here, I got that theta divided by alpha and beta. That would be theta plus 1 squared theta plus 2. That was why you have this guy here. Okay? That is what I now want to put them. I want to put mu. I'm going to put theta over theta plus 1 wherever I see mu here. And I'm going to put this guy wherever I see sigma squared. Okay? And that is what I was doing. That was what I was doing to finally arrive at this. So the variance is going to be this. If you try it out, how do I get this? What you're going to do, if you want to know how I get this variance, put this guy inside here. And the one for the mu, put this guy inside wherever you see the mu. Simplify. It will end up in this, has the variance. Now, if I now want to actually figure out the variance of my estimator, okay, the petroleum engineer want to measure efficiency of the refinery, okay, you need this variance. If you want to know whether the efficiency has gone up or gone down, you need this variance. Do you know that in 2020, okay, the final answer will now be this. Can you see that is the final answer for the? So it means the estimator is approximately normally distributed. So when you plug in all of that here, when you're done here, that will give you log theta. You can try it out. And when you plug in that, that will give you that. Let me also tell you where this can be used. In 2020, December 10, 2020, there was an article published in the Massachusetts Journal of Medicine by Pfizer company. Has anybody heard about Pfizer company? They claim that they've discovered a cure for COVID. And they claim 95% efficiency rate. Do you know if this guy here is their, give me 1 second. Let me use a pointer. If this guy here is their method, is their estimator, okay, then the mean is that, the variance is that. So if I now want to, as a statistician, if I want to go against them, if I want to say, okay, you've made a claim, and following a claim, there's always an investigation. If I want to investigate statistically, if I want to determine if the vaccine efficiency is 95%, I need the variance. And if I get a variance, I can get a standard error, because to construct confidence interval, to test hypothesis testing, we need standard error. And the standard error is the square root of the variance that we got here. So moving forward, asymptotic normality actually is a great deal. I put some other application here, exponential distribution. Let me tell you, this is very useful in survival analysis, where the waiting time before, the doctors need to wait before the patient get cured How long is it going to wait? That can, if this is the model is log reading of that. The underlying distribution will be exponential. Do you know, if I were you, why can't you try this? Why can't you try, apply that and see whether you're going to get this result? I put some other question. Look at that. When it's a square root, when you have a square root of that, this is the result that I'm going to have. Oh my God, I didn't solve this. Make sure you try to solve them. There are two major questions that will come out in the final that we have treated today as part of the area. On Monday, it's going to be our last day of lecture. On Monday, I'm only going to walk you through the final exam, practice, question. I need everyone to be around. Because on that very Monday, I'm actually going to... Okay, let's take a look at this. Should we have an in-person class on Monday, or we should have it on Zoom? If there is one person, just one person that say we should have an in-person class, we're going to have an in-person class. So what I need you to do, don't take your decision now. Send me an email. The lecture for Monday is revision. Do we want to have in-person? What I just need you to say, write in-person. If you want it online, write online. But the moment I see one student that say in-person, I will be here in person on Monday. That's all I got for you today. Make sure you all stay safe and have a lovely day. Bye for now, everyone.